So we've invented Euler's method to be a way to approximate solutions when we can't find an exact solution. But that kind of makes you wonder, if you could find an exact solution, how would Euler's method do? Would it produce points that are actually on the exact solution? Well, let's answer this question by taking a look at an equation where we can actually solve the equation exactly. So here's an equation we can solve exactly. dy dx equals y. This is separable. It also happens to be linear, so you can solve it any number of ways. In fact, this differential equation is simple enough that you can actually just guess a solution and have a pretty good chance of being right. All of the solutions to this equation look like some constant times e to the x. You can just check that if you differentiate that, you get exactly the same thing back again, so it solves this differential equation. The solution through this initial condition, 0, 1, we can find just by plugging in the initial condition. So 1 equals a times e to the 0. That tells us that a has to be 1, and that gives us the solution y equals e to the x. So to compare this to the approximate solution that Euler's method gives us, we have to actually run through Euler's method a few times just to get some points on the approximate solution. So we're going to start with 0, 1. So that means x sub 0 is 0 and y sub 0 is 1. We're going to use step size 1/2 just to have a step size to work with. So that means x sub 1 is 0.5. And incidentally, usually I use fractions, but when I'm dealing with approximate solutions, usually what happens is you get really messy expressions for your x and y values. And since it's only approximate, there's no reason to carry around huge messy expressions for your x's and y's, so you might as well just get decimal approximations. So I have a tendency to write everything using decimals when I'm doing Euler's method. So y sub 1 is going to be our old y value, which is 1, plus the function that is the right-hand side of the differential equation, which is just y. So our old y value again times our step size, which is 1/2, so 0.5. This gives us 1.5, so 1.5. So now we have 0.5, 1.5. Our next x value, we add the step size again, so now we're up to x equals 1. And then our next y value is the old y value, 1.5, plus, and then we evaluate this function again, so 1.5 times the step size. And then do the arithmetic on this, you get 2.25. So now we have the 0.1, 2.25. Now let's go up to x equals 2, I guess. So we're going to need 2 more steps. So x sub 3, we add the step size again, so that's 1.5, 1.5. And our next y value is our old y value, 2.25, plus our function evaluated at our old x and y values, so 2.25 times the step size, 0.5, and that is 3.375. So now we're at 1.5, 3.375. And finally, we get up to x equals 2. The y value that goes along with this is 3.375 plus our function evaluated at our old values, which is 3.375, times our step size, which is 1/2. And this is 5.0625. So our final point is 2, 5.0625. Okay, finally, done. So now let's actually plot these and see what it all looks like. So let's pull up GeoGebra, and maybe let's start by plotting a slope field for our differential equation. And the right-hand side of our differential equation was just y. And this is too many tick marks, so let's make them a little sparser. Okay, let's also plot y equals e to the x, because that was our exact solution through the initial condition 0, 1. Okay, So you can see we have our y equals e to the x curve. It's going through the initial condition, and also it's tangent to any of these tick marks that it goes through. And that's how you know it's a solution. Okay, now we can plot our approximate solution. So we started at 0, 1, but then our next point was 0.5, 1.5, and then there was 1, 2.25, and then 1.5, 3.375, and finally 2, 5.0625. Okay. Now you can see for all of these points, let me hide the names, you can see these points kind of follow the same general path as the exact solution, but they aren't exactly on the exact solution. Right? If you follow the tangent line from our initial point, which remember that's how Euler's method works, it just follows the tangent line. If you follow this tangent line, since you aren't curving up along with the exact solution, you're just going in a straight line, you don't go up quite far enough. And so that you get to this lower point instead of up to the orange curve. And as you move further and further to the right, this error sort of compounds on itself. So even though we are heading upwards, after just a few steps, we're actually a fair ways lower than what the exact solution is. So Euler's method, it does give you some idea of what a solution looks like, but it is not an exact solution. Right? Hopefully you are sort of catching the general trends of what the exact solution does, but you can't in general expect to get points that are actually on the exact solution. One thing you might wonder is, well, how can we make this approximation better? The reason that our approximate solution is drifting away from the exact solution is because our step size is so big. We go so far in a straight line before we sort of put our foot down on the slope field to get a new slope and change our direction. So one way to improve the accuracy of this Euler's method would be just to choose a smaller step size.